Okay, cool. I think everyone should be able to hear us online, I hope. Uh, good. Okay, cool. Great. So the speaker today is Govert Nijs, and he did his PhD at Utrecht University, then moved to MIT for his first postdoc, and now he's a CERN fellow. He was very involved in the recent light ion run at the LHC, and that's what he's going to talk about today. So thank you for being here.
Okay, thank you for the invitation. So I'll be talking about basically in general opportunities with new ions at the LHC. And this will be mostly based on, well, so for one on this paper about neon with all of these people, and then also about the neutron skin, which is by now a little bit old, but it has some kind of outlook, as well as a paper about the deformation of xenon, which will hopefully appear in the next couple of weeks. So in the last decade or so, Bayesian analysis has really transformed the field of heavy ion collision. So we're no longer just looking at a single observable and then at a single parameter and varying that one parameter to get the single observable right and then drawing some conclusion. We're really systematically looking at large amounts of data and in one go fitting all of our parameters that we have, or as many of our parameters as we can, to those data to really quantitatively try to understand all of our physics that we want to learn about. And so on the one hand, this also allows us to get these parameters very precisely, but also it means that we get very sensitive to details that were previously unimportant. And one of these details that was sort of became clear over the past couple of years that this is important is nuclear structure. So we have really started to see that if you really want to quantitatively describe your data of various nuclear collisions, you really have to take into account that these nuclei have some kind of shape. And you can basically use this connection between nuclear structure on one hand and heavy ion collisions on the other hand in two directions. You can either look at collisions that you've made at the LHC and extract what the shape of the nuclei that you collided is, or you can sort of engineer a system with a certain shape to answer a question that you might have. So in this talk, I'll basically do both things. So the latter will be, so engineering something with a specific shape will be this nuclear bowling pin story, and then the neutron skin and the deformation of xenon are about extracting the shape of something you collided at the LHC. So one thing I always like to start with is like the models that we use are very sophisticated. Like they're like Trajectum, for example, which we used, has 70,000 lines of code, but you don't actually need to know any of that. All you need to know to be able to understand what this talk is about is basically that hydrodynamics turns geometry into momentum space sort of geometry. So if you have something like this, that is the initial shape of the quark-gluon plasma that looks sort of like this oval, then since hydrodynamics is driven by pressure gradients, pressure gradient in this direction is larger than it is in this direction. So you get more expansion horizontally than you get vertically, which you then see in your particles that you detect in your final state. And in this way, the initial geometry of this overlap region imprints itself onto the observables that you can actually measure. And then with sophisticated Bayesian analysis, you can reconstruct what was going on. And also whenever a model parameter appears, I've tried to make it all green so that that's clear that that's a model parameter. So introducing how nuclear structure affects the heavy ion collisions. I usually start with a slide like this, which is basically how this sort of got popular, and that's with this star isobar run. So in 2017, I think, Rick ran both ruthenium-96 and zirconium-96. So these are nuclei with the same mass number. And one of them has 40 protons and the other has 44 protons. Now, the original idea was that basically only the charge would be different, so then the magnetic field in one system would be different from the other, so that you could look for the chiromagnetic effect. Now, that has so far not panned out. But there's something else that is different about these two nuclei, and that's the shape. So if you look at what these nuclei are supposed to look like, then I think this ruthenium looks sort of like this. So this purple model, and zirconium looks like this. So it's basically somewhat of a pair. And now if you look at predictions for example, the V2, then you can see that if you look at the ratio between ruthenium and zirconium, you get this very characteristic shape of the V2 as a function of centrality, which is quite well described by assuming that these nuclei have these shapes that you saw here in this purple model. No.
Sorry to jump in right
No
here,
worries.
but I mean, if you have a geometry that is not very spherical, it obviously matters how these guys are oriented when they meet each other, and that is not something that you can steer from the outside. That's just gonna happen.
Yes, exactly.
So this is then an average effect that you're talking about here?
Yes, so this is on average that you, I mean, you see this mostly in the central collisions, and because they're basically the overlap is 100%. Basically, every nucleon interacts. But then if you have something that's, for example, shaped like my hand,
you might not.
Yeah, here, it's not going to be central.
Yeah.
It's only going to be central if they're sort of aligned with each other.
Yeah.
And then, of course, they can still be oriented in some random way.
Yeah.
But if you look at multi-particle correlations, you can disentangle all of this. And
you can see the orientations.
You cannot see the orientations, but you can, but they do have an effect, which I will get to in the deformation of xenon.
Okay.
If I don't, remind me, because it's an important point.
Okay.
Oh yeah, and if anything is unclear, just interrupt me. That's completely fine. Another thing that is very nice about this is that sort of the details of how the hydrodynamic calculation work are not very important with respect to these shapes in some sense. So in this simulation, you can see that if you double the shear viscosity or halve it, or you double the bulk viscosity, then these individual orders for these V2s, they change by quite a lot. But the ratio stays the same, because basically this effect, if you change the shear viscosity, for example, it affects both systems equally. So then if you take a ratio, this just divides out. And actually, that's very insensitive to the particular value of eta over S. So one thing that I'll also mention is there are interesting things we think we can do with the LHC, then we should probably start thinking about that yesterday. Because it takes a lot of time to motivate these new systems, and getting something actually approved that it actually gets run is even more complicated. It takes a lot of time. You have to convince a lot of people. And then also the injector people need to make sure that they can actually do this. You cannot just tell them like, oh yeah, go do this isotope. They have to configure all of their machines to make sure that they can actually inject this into the LHC, which is also quite non-trivial. So there is some kind of time pressure to get this done, but there's also very interesting things we can do with this. So what I'll do in the rest of the talk is first I'll introduce Bayesian analysis, just so you get a bit of a hang of how this works, since it's so central to all of the other things we'll be discussing. I think it's important that I discuss this, and then I'll get to basically these three topics. So this nuclear bowling pin, the neutron skin, and the deformation of xenon. So Bayesian analysis is, in some sense, just a fit to data. You just look at how many standard deviations you're away from each data point, and you optimize the parameters to get that deviation as small as possible. In practice, this is a lot more complicated. I see it doesn't really render that well, but there's supposed to be blocks around this. I hope the other slides look okay. In principle, this is a lot more complicated because this is a very complicated, well, expensive thing to do. If you have a very high dimensional parameter space, you cannot just go make a grid through that, because if you have, for example, 25 parameters and you want 10 points in every dimension, then you have 10 to the 25 points at which you need to evaluate your model, which is obviously not going to happen. So how this works in practice is that you basically only evaluate your model for specific choices of input parameters. And then what you do is you take these input parameters, you evaluate your model, and you feed the inputs and the corresponding outputs to a Gaussian process emulator. And then that becomes a sort of fast surrogate for your real model that evaluates in milliseconds. And what is important about that is it's able, actually, this sort of Gaussian process emulator, it of course makes interpolation errors because it doesn't have the actual model data at every point, but it's able to estimate its own uncertainty, which is very important if you want to know how many standard deviations you're away from the data. So you do that, and then you combine that with your experimental data in this Bayesian calibration, which is basically a Markov chain Monte Carlo that runs through your parameter space, and that then gives you a posterior distribution that you can then analyze. So what this looks like usually is that here, don't worry about not being able to read the axis labels. These are basically 1,000 different model predictions for 1,000 randomly chosen parameter points. And you see that you get this sort of wide spread of different predictions. And then after you've done your Bayesian analysis, this sort of collapses onto the data points if you did this correctly. So then you fit it, and then this posterior that you get out of this is basically just a very long list of likely parameter combinations. And then if you project this onto, for example, a single parameter, like for example here, you can see that if you get some kind of nice peak, then this is constrained, and you can interpret this as like you can compute a 1 sigma error, and then you know what value you extracted. You can also look at things like correlations. So for example, here you can see, if you look at a 2-dimensional projection of your posterior, you can see that this is quite correlated. In principle, you could also look at higher correlations, but they're hard to plot. So this is then what you basically have. Now, what we use in our calculations are basically these 670 individual data points, and this is more of a slide to motivate that we're trying our best to do as much as possible. So basically here, green means that the data exists and that we fit to it. The clock, I couldn't get an hourglass. It somehow doesn't exist in this library. But so the clock means that someone measured it, but we don't use it. And red cross means it doesn't yet exist. So we're really trying to sort of fit to as much as what is experimentally available as possible. Now, what can you do with this? And there's sort of 3 main ways in which you can use the Bayesian analysis. The first is that you can you have a parameter which really encodes for something in your physical model that you're interested in, like for example, shear viscosity, and you can just literally extract that shear viscosity and plot it. Now, another thing you can do is something called parameterized phenomenology. I call it that. And that's that you can basically have, you can introduce a model parameter that sort of interpolates between different behaviors. So in this case, looking at how the initial condition combines 2 different thickness functions. So you have 1 thickness function for each nucleus. And different models have different behavior for how this scales. So this P parameter, if that's 1, for instance, it just takes the average of these thickness functions. You get this wounded nucleon model. There's also KLN model, which has something like -2/3. And then IP glassband and EKRT scale like this being approximately 0. Now, if you compare the posterior, you can see that it's very nicely peaked around 0, which sort of rules out these 2 models and seems to be compatible with this with IP glassband and AKRT. So then you can conclude that probably those 2 models are doing something right. that those two models are not doing that. And the last thing you can do, you can actually make quantitative predictions. So we can actually so this is a systematic uncertainty for varying all the parameters in the model according to what the Bayesian analysis allows. So after fitting, this is the remaining uncertainty. Now you can see it's quite narrow, so we're quite apprehensive about sending this to CMS because then they measure something that's probably different. But then you can see that it actually is spot on. So it seems like we're really having some predictive power, and it's not just fitting. And then of course you describe everything because you fit to it. You really can also make predictions of things you didn't fit to. Now, with this, let's get to the first.
How do I think about this? It comes out of a fit, right? I mean, there is predictive power partly in the models. There is a huge amount of constraint because you have such an enormously large amount of data to feed through those. That you probably link those parameters together very, very strongly. I mean, this is a different thing than predicting through a theory. There's an extra step in there somehow, and a mentally catalog was probably.
Well, I mean, of course, there are some trivial things you could predict, like, okay, I'm going to fit to the 0 to 10% bin, I'm going to fit to the 20 to 30% bin, and I fit the bin and I predict the bin in between. Of course, I'm going to get that right.
Yeah.
So that's sort of trivial. Yeah. But then it's also possible to get this wrong. Like, for example, I don't know if you followed this story with this Q parameter we have introduced. Anyway, so basically what people were previously using was a Q parameter that was implicitly 1. And then from our fit, we found that it should be closer to 4/3. If you don't do that, you get this completely wrong.
Okay.
So then if you use the result from that Bayesian analysis, and then you...
Are we uncovering correlations we are not aware of? Is that a way to describe what you're talking about? Between nominally, right, things we thought were intrinsically independent of each other are now linked.
Yes, I guess you could say that. Yes, that I see it as that the model apparently is well, we describe at least the phenomenology of the model well enough that you can feed it something that looks unrelated and get a precise constraint for it, or a precise prediction for it, and then have it actually agree with the. I mean, that shows you that at least you think you have the phenomenology right, or at least the relevant phenomenology for this.
Right. Don't get me wrong. I find this amazing. I just tried to catalog how you should think about this.
Okay. So
sorry, actually, I have a question also related to one. So in the training set for or in the data that you constrained the model on before you made this prediction, was there no ultra central data at all? It's kind of strange that it even is so constrained, because I could imagine that once you saturate your geometry and then you get these ultra central collisions, it's sort of you could have many models with different physics that that all fit the data that you use, but they would make quite different predictions, or maybe it's just Hydra is quite constrained.
Well, I mean, this depends mostly on your initial condition. So the amount by which it goes to the right before you stop having any collisions, that is sort of governed by how much fluctuation you have in the initial condition. Other than that, this is mostly, of course, the equation of state that is important, but then we get that from lattice QCD, so we're pretty sure that that's probably right. And there's a lot of details that actually do matter a lot, but I can talk for an hour if I go into that. Okay, so then I'll move to the first topic that like the meat of the story, and that's this long-standing question about whether collective phenomena that we see in small systems such as PA and PP are hydrodynamic in nature or something else. And so basically we've seen these flow phenomena, which in AA collisions we interpret as being hydrodynamics, and we see these same signals in PA and PP, which of course brings a big debate, which to my knowledge has raged since like the 2010s. And well, you can basically the question is, do you form a QTP here? And is this hydrodynamics? And I think a good place to start is, well, for one, of course, this is not really a binary yes or no question, but I took that slide out for time. But like, it's good to take a step back and to think about why we think that lead is hydrodynamic. And I think an important point is that we don't just measure a V2 signal. We know where it comes from. So thinking back about my story about that you turn the geometry into momentum space anisotropy, we understand that for lead because we know that for central collisions the overlap region looks like this, and that for peripheral collisions it looks like this. So you measure the V2, you understand where it comes from, so you can sort of draw the conclusion that it's really the geometry that is causing the V2, which would then point to hydro. But then for P-lead, we don't really understand this very well because we basically don't know what the initial geometry is. So you can also not make this argument with something else. Then a large part of the shape of the overlap region is basically what the shape of the proton is. Now, this is something that, to my knowledge from theory, we, at least at this moment, do not know how to compute. So you know more about this than I do, but to my knowledge, we cannot do this. But it does matter a lot. So if you look at this calculation, you see that if you have a round proton, so basically just a single Gaussian, then you get a much lower V2 than if you assume that it has 3 hotspots. So this is important.
This is the other thing, right? I mean, the original pictures, the input that you're running, hotspots or no hotspots, what goes into that? Because if you're thinking hotspots in a proton, you should also think hotspots everywhere else.
So we take this as a model parameter, like how many hotspots there are, and also the size of the hotspots. And we vary it in the Bayesian analysis. It's not very constrained, but then our predictions that we make.
But you get some constraint on it?
Very little.
Okay.
We're about to change that, hopefully.
Okay.
It turns out that the row 3 observable is quite sensitive to the number of hotspots in lead. So then if you fit to that, you can constrain, or no, the size of the hotspots. So we hope to get some meaningful constraints.
Okay.
Out.
Very interesting.
But yeah, so then all our predictions with the systematic error that I said, that we look at the parameter uncertainty and how it propagates into each observable that we predict. Our lack of knowledge of how many hotspots there are and how large they are is included in that uncertainty. So yeah, basically what this means is we can describe the data, but only if we make sort of the right choice. But then you can ask, like, did you just make the right choice because you saw the data? So you're no further.
So no, you've posed the question. You are further.
Yeah, you are
further. Posed the question. You haven't answered it, but you've posed the question in a different way.
Yeah.
So the round proton,
just a Gaussian blob of stuff.
So there's no substructure.
There's no substructure.
I mean, right, this is in the context of Jim Walk or decay working for Hera, which is talking about saturating this thing with gluons inside, right? I mean, this is the context for that.
Yeah. So another reason is that we usually do 2+1 dehydro simulation. So we assume boost invariance, and we basically do this out of necessity because we don't really understand very well how the longitudinal structure of a collision works. We're hoping to change that, but that's a work in progress. And right now, we don't know this. The problem is that P-lead doesn't really have a nice plateau where boost invariance is a reasonable assumption. So it's not really clear that you can use this for P-lead.
Moving this way.
I think so, but don't quote me on that. It doesn't really matter. I mean, in any case, it's not flat. And there's another problem here that if you look at the the event planes, the event plane twists as a function of the rapidity, which also is something that you can only really describe if you have a 3D simulation. So, well, this is probably a problem we can overcome at some point, but not right now. So what you want to overcome these two problems is basically you want to look at a system where none of the projectiles is a single proton, and you want to look at something that is symmetric, so that it has, by symmetry reasons, has a plateau around mid-rapidity. Now, using that, let's try to propose a precise question. So, can we find a small system? Because we want to test whether a small system is describable by hydrodynamics. And we want to describe the small system with a hydrodynamic model, which also simultaneously describes lead-lead. Of course, I could describe the small system and then tune the parameters to describe the small system, but then I would consider that cheating. That's not really answering the question. So then basically, this Bayesian analysis framework provides the perfect opportunity to do that, because you can just say, like, okay, we know what the parameters are, they're constrained by Bayesian analysis. Let's try to predict something for a small system. So what we want is small sensitivity to proton substructure, no longitudinal structure issues, so a symmetric collision, and we want whatever we're going to predict to be, well, sensitive to whether there is hydro or not, and we want the uncertainty to be quantifiable and small. And for, well, you can look at, for example, what you see for OO, because that's a nice candidate that, I mean, it's symmetric, none of the things are a proton. So you can make these predictions for the V2. And here, these bands are, again, our full systematic uncertainty. And you see that you get this uncertainty, which goes from like 4% here to maybe 14% here. So we can describe this with, well, we can quantify the uncertainties, and the uncertainties are, well, I don't know if you'd call them small. At least you can quantify them. And if you look at now, so I'm going to zoom in a little bit on this most central bin. And this central bin is made up of the spread, so that this band is made up of the spread of 20 different randomly drawn parameter sets from the posterior. Now here, what I'm going to draw is these 20 different predictions, right? Individually. And I'm going to draw them as a function of the number of constituents of the proton. So I'm just making a scatter plot of this. Now, you see that there's no real order to this, right? It seems uncorrelated. So from this, you can sort of see that there's no real dependence on the number of hotspots anymore, because, well, otherwise you would see some kind of correlation. Also, from work by Chen and some other people, you can see that this longitudinal decorrelation is much less of an issue. So they have a 3D code, and they find that it's much less of an issue than with BLED. Now, one thing you can ask is, can we do better? So here I'm showing the same thing. So again, the central V2, but now as a function of the nucleon width. And you can see that here there's some clear structure, right? You see that this is negatively correlated. So our uncertainty in this guy propagates to our uncertainty in V2. So, and similarly, the sigma flux, this is basically a Trento parameter which encodes the amount of fluctuations in the initial condition. You see that this has sort of a trend like this. So also these fluctuations seem to be important, and they are actually these two are the dominant contributions to why our uncertainty is the size that it has. So, but one thing that you can remember from the introduction, like thinking back to this isobar run, if you look at two different systems systems that are close in size, and you divide, you take ratios between their observables, then many of these things cancel. So can we exploit this fact to try and come up with some other observable that we can predict more precisely than this? And for that, it turns out that neon is one of the best things you can do, basically. So it turns out that for small, so this is basically what you get out of this PGCM framework, and this is basically the one-body density of what one of these nuclei looks like. In this case, oxygen, you see that basically 4 alpha clusters. You'd expect them to be in a perfect tetrahedron, but they're not. They're like slightly squashed. But you can still see this is very close to spherical. And then neon looks like this. It's basically a bowling pin. And it turns out it's by some measure the most deformed nucleus in the entire nuclear chart. So what you can then use is that well, oxygen is almost spherical, and this is very much not spherical. So then if you collide them and you have perfect overlap, so in the central region, then you expect this to produce a very large V2 compared to oxygen. And then, so basically what you get as a prediction is are these curves. So you have oxygen in blue, neon in red, and you clearly see that you get, as you go to central collisions, you open this gap. And if you look at the ratio, you actually see that you can predict this quite precisely. So most of these uncertainties in these bands are actually shared, and if you take a ratio, it just drops out. And you can look at this more clearly if you look at the relative uncertainty in the V2 of neon. If you look at the relative uncertainty of the V2, and I plot 2 things. So the relative uncertainty of the V2 of oxygen data, and that's this blue curve. And then if you look at the neon to oxygen ratio, you see that you really get to like 1% uncertainties for like a very large range in centrality. So you can really predict this very precisely from the model. And similarly for the rho, which has not yet been measured. And so the rho 2, you basically drop the uncertainty by a factor 5. Now, if you look back at this wish list that we made, you see p-lab basically fails everything. And for OO, you see that it has check marks and that you can reach like 4% uncertainty in your prediction. But then if you in addition to OO also have neon, you can get to 1% on the ratio. So now the nice thing is that somehow we managed through a year of lobbying to make the LHC actually do this. And what I find very nice is that you can really see that these hydro predictions for OO and neon both, they basically go through the data points for everything that Elise measured. But you also see that you generate some new questions, which is exactly what we wanted to do to help the debate along. Because for example, this one, you can see that NLEFT, so that's one of our models for nuclear structure that we used, that describes the Alice data very well. And PGCM sort of undershoots it. But then if you look at the ratio, well, they're both sort of overshooting it. But PGCM is now closer. And I think what is also interesting is that IP Glasma, I didn't show this in the previous plot because Alice didn't put it in. But IP Glasma gets sort of the best fit to well, it's not a fit, it's a prediction, the best description of the data, but then it's basically too flat. It doesn't really have this rise at all, but also it doesn't get the absolute value right at all. So it completely, I think, undershoots it. So But then that's really genuinely new information that we can use to improve our understanding of these initial condition models. And what I like to think is that basically, if we had only had this, then we would have concluded that everything is fine. We go through the data points at 1 sigma, and because we have neon in addition, and we can look at this ratio and see it doesn't match, we know that there's still some things we can learn, which is precisely what we wanted to do. And I'll briefly flash through this, that of course, well, you do this for one reason, but then you get a lot of other things as well. So you get the multiplicity, we got the RAAs, which for some reason path lengths seem to describe very well. I don't know why. This is the best model for it because it's extremely simple. But it seems to be the best at describing the data. So I think this has been very productive. I'll also check how I'm doing on time. Yeah. But now let's move on to the next topic. So and that's this neutron skin. So the reason why this is interesting is that it turns out that for large neutron-rich nuclei, the neutrons sit further from the center than the protons. And this is very sensitive to basically the interparticle forces. And those same interparticle forces are what drives the equation of state of a neutron star. So basically, if you measure one, you learn about the other. And you can basically draw a one-to-one correspondence to the value of this neutron skin to the radius of a 1.4 mass neutron star. So how you define this in like a precise way is if you just look at the RMS ratio, RMS radius of the neutrons, RMS radius of the protons, you subtract them. By definition, that's your neutron skin. So how do you measure this? Well, there's two things you need. You need the RMS of the proton. Neutral. Not only that, the lowest order moments are also zero. So electromagnetic scattering doesn't really help you. So one thing that people have done is to use polarized electron scattering. And then because it's polarized, you can distinguish what is a W a Z mediated scattering and what's a photon mediated scattering. And then you can, from that, you can figure out what your proton and neutron interactions were. This is very, so for example, in the US, they've built a dedicated experiment called PREX in Virginia that is, well, purpose-built for this reason. But it turns out that with heavy ion collisions, we can provide a completely orthogonal method. So it's basically, we're measuring the sort of the total shape of this thing, the total size. And then since you know the proton RMS, you can sort of infer what the neutron RMS has to be to make this work. And it's also completely gluonic. So this PREX is like electroweak, and this is a completely different interaction. So it's sort of nice and complementary. So how do we do this in practice? Because we're going to use a Bayesian analysis for this. What you have to do is you have to somehow parameterize your neutron skin. So what we use is the Wood-Saxon distribution, where you have this R and A parameters. And what we do is for the protons, we fix them to these well-known values. For the neutrons, we fix this R value, which is motivated by theory calculations. But basically, the reason we didn't vary both of them in the Bayesian analysis is that, well, we didn't know this was going to work at all. And the more parameters you have, the more difficult it is. So we decided to start with just one parameter. But then this A parameter is AN. So it's basically the skin depth of this neutron, of the distribution describing the neutrons. That we vary in the Bayesian analysis as a parameter. And then you can compute what the RMS is as a function of well, this by just integrating it. Well, I cannot compute this, but Mathematica can. And then if you look at the neutron skin as a function of this AN, you see that it's basically almost this linear relationship. So basically, if you constrain AN, you constrain the neutron skin. Now, do you have something that is sensitive to this? Because if you're doing a Bayesian analysis and none of your observables depend on your parameter, then of course you're not going to constrain your parameter. So one thing that is sort of obvious, so here I show basically an overlap region where the neutron skin is taken to be small, and here below it's taken to be large. So one obvious thing that changes is the cross section. So this is this up here and also up there. You can see obviously if you make your nucleus bigger, your cross section is going to increase. Makes sense. But also you see that so you make the size of the thing bigger and of the overlap region bigger, and you also make it slightly less elliptical because you're basically buffing up the sides. Now, what this is going to lead to is, so you have some kind of dependence of the multiplicity on your neutron skin parameter. And you also have a dependence of your mean PT. This is sort of easy to understand because if you make the overlap region bigger, then your pressure gradients are going to decrease and they drive your expansion. So your mean PT is going to decrease if you increase the neutron skin, which is exactly what you can see in the plot. Now, also for V2, well, you saw that it's this is basically puffed up and it's less elliptical. So the larger neutron skin leads to a less elliptical initial state. And then, of course, the V2 is going to go down. So in view of time, I already took that slide out. Good. So then if you do your whole Bayesian analysis, you find you get this constraint, which is quite nice because you see that you're sort of competitive in error bar with P-Rex, which is a dedicated experiment that costs like several $1 million, I think several tens of billions even. And you can see that it's compatible with other methods. So that's a sort of nice result that you're basically able to do this with data that's all just on HEP data. You can just download this and run it and you get this. Now, in this I'll actually skip in view of time. Now, one thing that would be interesting to do in the future is that P-Rex actually has a sister experiment called C-Rex, which measured the neutron skin of calcium. So calcium-48. So calcium is a sort of a special nucleus because it has, or a special element. It's the only element that has two doubly magic isotopes. So you have calcium-40 and calcium-48. And so doubly magic means they're approximately spherical. But now, what the thing is that if you look at these nuclear structure models, they sort of seem to have some kind of tension with what P-Rex and C-Rex measured. So it would be very interesting to do this in the LHC as well to see if we get the same tension or maybe not. And what would be an additional benefit is that if you collide both calcium-40 and calcium-48, then you would get very sensitive to the difference in for electromagnetic effect, but it's tiny. So basically, if you measure both of them, and you know that calcium-40 has no neutron skin, then you might be able to get a very tight constraint on the neutron skin of calcium-48, which would be very interesting to have. But then to motivate something like this, you would have to first show in a simulation that with mock data that you could actually get this precision that you promise. Otherwise, you're never going to run it. And also calcium-48 is extremely expensive. Yes. Well, I mean, you wouldn't have to completely have isotopically pure calcium-48. So apparently that would cost the GDP of the world, according to Reyes. So that's unfeasible. But even if you have like slightly enriched, maybe you have 10% calcium-48, then you lose 90% of your luminosity, but like you don't need that much anyway. So this is something that would be quite interesting. I'm going to skip this in view of time. Moving on to the shape of xenon. So this is something that we can do with existing data because this is something that the LHC ran. So here we're basically going to do the same exercises with lead, just with different parameters. So now this radius in the Wood-Saxon is no longer just a constant. Now there's a radius parameter which I forgot to make green. There's also expansion in terms of spherical harmonics, and you have this quadrupole deformation beta 2 and the triaxiality gamma. So triaxiality means basically that you have three axes that are all of a different size. Now, well, what you can see is if you make this beta 2 bigger, then you either make your nucleus prolate or oblate, depending on the value of gamma. And this deformation enhances the V2. So you see that this is a measurement by Alice, and this is the ratio of V2 in xenon over lead, and you see that you have this clear enhancement in the most central region. Now I'll get back to your question, because it turns out you also need the rho observable specifically to get the gamma. And here the orientations come in. So if you have gamma which is 0 with a non-zero beta 2, then you have a prolate nucleus. If you have gamma that is close to 60 degrees, then you have an oblate nucleus. Now, what happens if you start randomly going over the orientations, then if you have, maybe you can clean this if I write on it, right? It's not that bad.
It's
okay.
Let's move on.
Last time I gave this talk, I actually brought fruit, like a mandarin and a lemon and a kiwi to illustrate this. But so basically, if you have a prolate nucleus, which sort of looks like this, then imagine that it collides like this. Then the overlap region looks like this, so it's elongated and relatively large. If it collides more like a cigar, like head-on, then it's small and spherical. Now, if I have a prolate nucleus, an oblate nucleus, then, well, if they collide sort of like this, then it looks like this. But if it collides like this, it's spherical and large. So what the rho observable does, it's a correlation between the V2 and the mean VT. Now, in this case, the mean VT is going to be large because the system is small. In this case, the mean VT is going to be smaller. So in this case, the V2 correlates with the mean VT, I think. Might get the sign wrong, but and in this case, it does the exact opposite. So by looking at the sign of the rho observable, you can distinguish between these two extreme cases and, of course, everything in between. So you don't really see the orientation. You still average over it, but if you, in principle, if you look at high enough moments,
You see a
you
correlation.
can, yes. I mean, of course, the higher you make the moment, the more statistically difficult it becomes. But
Absolutely.
I hope that answers the question.
This is actually more powerful than I expected, honestly, but of course, it needs to see our bars in the end.
Yes. Yeah, so basically this is basically what we fit it to. We still have to clean the plots up a bit to make them look nice, but basically you can see that for these, for example, for the rho observable, you can see we really go through the data points very, very nicely now. So we basically fit to lead, xenon, and ratios and differences. Now, one thing I will actually spend some time on is that the details are important. And especially for something like this rho observable, it depends very sensitively on like getting the comparison between theory and experiment exactly right and making sure this is apples to apples. So what I show here is, well, first, these are sort of the bins that we use for the fit. But then you could imagine just computing your rho observable in these wide bins. But then it gets a centrality dependence, right? Because you're basically no longer just looking at the correlation at a fixed infinitesimal centrality. You're looking at some wider centrality bin. So actually, if you go in smaller bins, compute the rho observable and then average, you get a different result. And going in the smaller bins is actually what Alice does. So it's very important, or Might be Atlas. I think it's Atlas. Yeah, that's actually what Atlas does. Very important to get that right, because otherwise you're not going to get a good fit. Another thing that's important is how you
Was that clearly in the papers that you had to compare to, or what did you have to dig for this?
I think this took Wilke a month to go through, like Atlas was really diligent in putting like 400 plus data tables on HEP data. And he went through all of them to find the one that we could best compare to, given the limitations of the model. Easiest to do is charged particles at mid rapidity, just counting. Of course, that gives you some autocorrelation, but you get that in the theory, you get that in the experiment, still apples to apples. If you have something very far forward, you need a good 3D model to describe that well. Not very good for us. So for us, the n charge at mid rapidity is the best one. You can see that that actually makes quite a difference if you make different choices there. So, well, this is all worked out now, and we are really comparing apples to apples as best we can judge. So, well, we're really happy with how well it fits now. Now, if you look at the result, you see that we actually think this is the first sort of experimental extraction of the neutron skin of the xenon. To our knowledge, no one has done that before. And what is also quite interesting is that in the inset, you can see the correlation between the neutron skin of xenon and the neutron skin of lead. Now you can see that we're basically sensitive mostly to the difference between the two. And you should keep that in mind for a few slides in the future. And also for the deformation parameters, it's beta just say that it's plotted, it's like 1.8 sigma away, so it's, I still call that fine. And given that this is neither 0 nor 60, means that it's truly triaxial, so this thing has 3 differently sized axes, which means that it's shaped like a kiwi. And this is ChatGPT's impression of what a relativistic kiwi collision looks like. Now, why is this important? Because you might think like, well, so you measure the shape of xenon, we don't care about that. It turns out that this is important in a process that I'm about to introduce. So for certain nuclei, they sort of have to undergo beta decay, but they cannot because sort of the potential, well, the mass of this intermediate nucleus is too high. So it cannot actually undergo a single beta decay, but it can undergo double beta decay to a nucleus that is 2 spaces away. Now, this is, of course, very slow because it's requires 2 W bosons. But it does happen. And there are several nuclei that decay in this way. So Feynman diagram associated to it is this. So you can see that there's 2 neutrinos going out. But if the neutrino is a Majorana particle, then you can also draw this. And in this case, you would emit no neutrinos. But it's only possible if the neutrino is Majorana. How you would see this in practice is that if you look at the spectrum of the electrons coming off of this, then double beta decay, and then the neutrinoless double beta decay, since there's no momentum going into the neutrinos, would appear less some kind of delta function peak at the end. So this is what experiments are actually looking for. They're trying to see this peak. Now, the decay rate of this process turns out to be given by a formula like this. So you have this effective Majorana mass of the neutrino, which is what people are interested in. But then the decay rate is also proportional to this nuclear matrix element. And that's something that from a nuclear theory perspective is extremely difficult to compute. It's difficult as in, I didn't put that slide in, but like there's basically order of magnitude uncertainties on this. So I've seen, I have a slide somewhere on my laptop where basically you can see this guy is like between 1 and 10. So basically this is obstructing being able to extract this guy from this guy. Or presently putting an upper limit on this guy based on an upper limit on this guy. Now, what it turns out is that there are correlations between the difference in deformation between the parent and daughter nuclei and this nuclear matrix element. So what that means is that if you were to measure the difference in deformation using the methods that I just showed for xenon, then you would be able to constrain these nuclear matrix elements, which would be interesting of neutrino physics. And what we are currently trying to do is to sort of work this out for this particular decay, and there's some other decays that you can also look into. But then again, it's the same story. We would, like, if we were to motivate that this is interesting to do, then we might want to collide this at the LHC at some point. So basically, well, since I'm out of time, I'll go very quickly. So we're able now, with our Bayesianized understanding of how these collisions work, we can really like start looking quantitatively at all of our data, and that leads to qualitatively new results. So we can really, like, previously we didn't even know that we could do things like extract a neutron scan. Now we can do this. And we can also leverage the shape difference of something like neon to the shape of oxygen to really answer questions that we've had for a decade, well, not decades, but a decade. So I will end with basically the power of short runs. So this xenon run that we had, it's just 6 hours of data taking. It doesn't take anything away from your statistics for lead or from PP. But this has generated an enormous amount of papers and showcases that you can look at these shapes, you can extract these shapes, and that they are useful for something. Similarly, this neon run only took 12 hours. And wow, so we find that hydro broadly works, but there are some details that we don't quite understand yet, and we can build on that. So, well, one thing that I would like to see is for the experiment to measure this. But then also you can ask, like, should we go smaller? Maybe we can do alpha alpha and see if hydro still works there. Maybe you see even larger deviations. Would be interesting to do. The machine says they maybe can do alpha alpha. They're not sure they can inject it. But then also there's several other things we could try, like this germanium and selenium. We can do this calcium-48 and calcium-40 thing. Magnesium I put on there mostly because it's available. I don't really know of a physics case for it, but the injector people keep coming to us like, we can do magnesium. Do you want it? Like, I don't know. So yeah, I'd like to end on the note that like a big thanks to everyone in the experiments who made this happen, because I think this has really changed how theory and experiment interact with each other, that we can really use our theory knowledge to see what would be most interesting to do experimentally. So I'd like to thank you for your attention.
Thanks. Questions? I guess there were like questions during the talk, but are there more questions?
Yeah, coming back to how the experiments define centrality, have you looked at how they do it?
Yes.
In terms of the Glauber model, using the Glauber model to
for the anchor point.
Categorize the centrality. And how does your theory compare to a Glauber fit to the data?
So what we do is, I mean, the Glauber fit, well, there's a couple of things to defining centrality. There's like what you use, like forward ET or mid rapidity and charge, or like several different things. You can use the CDCs in some cases. So we try to simulate as best we can what the experiment actually did. For Alice, it's a bit difficult with, for example, the V0s because they're very far forward. We don't really have a working 3D model yet. So we cannot really accurately simulate exactly that. And then there's the anchor point for which the Glauber model is indeed used. what we usually do is we actually vary the anchor point in the Bayesian analysis ourselves. So we vary the, well, what is 100% centrality? And well, what we get out of the fit is actually that it's 100% with some like 3% error or so, which would indicate that the centrality that, that the anchor point that, for example, Alice uses is compatible with what we say it should be to be able to fit the data. But yeah, so all of these things, we always try to do this as precisely as possible in the same way as the experiment. So we also talk with the people who do the measurements and to try and make sure that we're not making some details differently.
I think for the deformed nuclei, it becomes really important, or more important than for a spherical.
That I don't know. But then also the precise anchor point. Well, so if you're looking at it that much, so for the purposes of extracting these shapes, this probably doesn't matter that much. But of course, we still try and do it correctly.
So if I imagine some arbitrary model with 20 parameters and I go and try and do some hard Bayesian analysis and I'm able to fit my model to data, and somehow maybe if I'm really clever, I'm able to extract a neutron stream as you did in your model. What I've done there is basically come up with a really complicated way of drawing lines to the data points. But I haven't learned anything about physics of the experiment happening. And I wonder, in your model, you have parameters and you're fitting them to the data, and you go and extract this neutron stream. But if I use a different model, I get a different extraction. So how valuable is it to actually go and do these sorts of Bayesian analysis if I want to learn something about physics?
Well, so it depends, of course, what you put into it. But I mean, how much you can learn in terms of physics also depends. Like, for example, for hydro, we know very well how a hydro expansion works. You can just write down the derivative expansion and you know exactly what the transport coefficients mean. So if you put like eta over S as a parameter, you know exactly what that means if you extract it. Now, like other things, like for example, how the pre-hydrodynamic stage works, well, we don't really know. So what we try is to find something that at least phenomenologically works. But even then, you can try to do something where you learn something. So for example, what we use in these analyses, for instance, is a pre-hydrodynamic stage which interpolates between free streaming and a holography-inspired model. So then you just have a parameter that's sort of the interpolation between those two models. So then if that thing says, like, I want the free streaming, then you maybe learn that free streaming is how the dynamic stage works. It's not what it says. It says, like, I want the holography model. That maybe tells you that your pre-hydrodynamic stage is strongly coupled. And of course, you don't know really what the correct model is, but you can still try and like look at different approaches and see and try to learn from that.
It's always a tricky thing. I mean, some of these statements are possibly model independent, just the way the analysis was done. And others would be model dependent. So exactly. How easy is that for you to suss out in these situations? Because this might be a case-by-case assessment that you need to do.
Yeah. So, and that's also, well, we're trying to be very, very careful about this. So, of course, you can never go outside of your own model. So you cannot see what would happen if you had used a different model, except to just try it. But what we do is to check for example, correlations. So if two things are very correlated and we are interested in the one thing, but we don't really know that the physics of the other thing are correct, then maybe we don't publish the thing we extracted. And also what we try is for robustness, we can just fix parameters at unrealistic values. So for example, you just take the, I don't know, the nucleon width and you say it's like now it's 1 Fermi, or it's 0, well, not 0, but like very small. And then you see like the result I want to publish, does it change? If it completely moves around, then you don't trust that it's robust. But if it stays the same, regardless of if you do unrealistic things with the other model parameters, then probably it's relatively insensitive to what you do. So we do check all of those things before writing a paper to avoid embarrassment.
This is the usual problem, right? If you try to get intelligence out of numbers, if numbers is the thing you have to talk to, that's always harder than if you have a calculation that says this goes in, this structures the result this way. And you're in essence always open to overlooking something somewhere.
Of course,
well, if the more circumstantial evidence you collect, the better it looks.
But I think what is also a thing is this is already a lot better than what people were doing previously. Like,
absolutely.
I mean, it's not perfect, but yeah, you can at least you have your errors under some quantitative control, and you can try and do the best you can.
Your error shrinkage observation that you have in this actually gives you way more control over this, right? And this is really the big thing that enables the whole discussion.
But then also that's enabled by the Bayesian analysis, because otherwise, of course, it's an obvious statement. Of course, if I know that my V2 is proportional to my 8 over S, then of course, if I divide, it's going to drop out. But then Bayesian analysis allows you to really make that quantitative and really show like, yes, it drops out. And not only does it drop out, it drops out to this margin. So yeah.
Other questions?
Okay. I mean, why go down in mass if you don't understand the high multiplicity proton data? I mean, isn't there already enough that we need to first understand before we can motivate systematics? Why would you need extra neutrons, for example, to tell you more?
You mean extra neutrons?
Yeah, in your nucleus.
Yeah.
I mean, the proton is already a nucleus, if you think about it. So, I'm still not convinced. Why would you need, for instance, alphas on alphas?
Well, I mean, what that would be is something where, in contrast to like proton-proton or PA, you would have the same advantages as you have with OO. Everything would be under quite good theoretical control, but it's one rung lower, because now we see that for OO, hydro works reasonably well. So it makes sense, at least to me, that like to try and see how far you can push this. If you push it lower, does it still work? Do the discrepancies become larger? But it's also because we were asked, like there's a workshop next week at CERN where, well, the question is basically that people are interested in doing something other than given that they want to do this in like June next year,
Because then the LHC stops after June.
So they need to.
It depends how good this net run finishes. At the moment, doesn't look good.
Yeah, but yeah, so we were also asked at very short notice to provide something. So Juliana and I went to an LHCC meeting a few weeks ago, where actually the machine people discussed the options, and it turns out it's basically they can do OO for a week, or they can do or 00 for a month. But then I would not be very interested in that because like I don't know what you would get that you don't already have by just increasing the statistics. And then the only thing that they theoretically motivated would be the alpha alpha, yeah, or the magnesium, but I don't know why. I mean, of course, I wouldn't object to having those data, but like I wouldn't be able to motivate it. And at least the alphas is something that I can see some argument why you would want to do this. One thing is also that's relatively risk-free, because for example, say they were going to say, we're going to do germanium, then whether that's interesting or not depends very much on our ability to extract the relevant parameters. So what if they collide that, and then we say, yeah, sorry guys, we didn't deliver on our promise. Then we have a big problem. But this alpha thing, it's sort of regardless of whether it's hydrodynamic or has deviations or is completely different, any of those answers is going to be interesting. So it's relatively risk-free. The machine people can maybe do it. And I think the other options that they have are just not terribly interesting, I think.
So is the alpha particle the only thing between proton and oxygen that the LHC can do in size?
Yeah, they can probably do carbon, but it's very close in size to oxygen, so you're not really going down in size that much. The problem with alphas is that so they're constrained to something that has the same charge over mass ratio as something they've already collided. So that basically means it needs to be isospin symmetric. The problem is that for the alphas, if they were to completely strip it of all of its electrons right away, then in Lear it would produce too much radiation, which would be unsafe, and they would have to rebuild Lear basically. So they cannot do that. So the only other option is to strip only one electron and then strip the second one later. But then if you do that, then apparently for helium, they know that the cooling of they need to cool these beams so that they have all have the same momentum. And the injectors work on a 1.5 second interval of injecting into the PS. And for helium, if you strip only one electron, then the cooling time is 9 seconds. So probably if you start injecting that, you lose a lot of luminosity. Now, if you're just looking for some flow data, maybe you don't really care that much that you lose a lot of luminosity. Maybe it's fine. But so that's why they're not completely sure that they can do this in a way that would be useful. They're also not completely sure they can't. So
so we don't see flow in proton-proton, or do we?
Well, I don't know. I mean, you see a V2, whether that's flow, yeah. I don't know. Maybe.
Because if we do see flow, then it answers the question.
Yes, but the problem is that there you don't know what the initial geometry is. So that's why I would say something like alpha alpha would be interesting to see sort of the transition region between.
Geometry, you mean the nuclear geometry? Or...
Well, in that case, it would be the proton's geometry.
Well, we have PDFs.
Yes, but that doesn't, I mean, yeah. I think if that were true, then there would have been no debate. We would have settled on whether this is hydrodynamic or not like a decade ago.
Yeah, well, you need to have something more than just excellence. You need transfer structure. So,
I mean, the geometry is small, is microscopic in this case. While in a nucleus you have a macroscopic geometry. You have alphas. You have neutron protons.
Yes, but that's something they can compute. So they can compute very well what the configuration of nucleons in a nucleus is. I mean, it's not easy, but they can do it. They can look up an effective Hamiltonian and they can put it on the lattice and actually compute it.
and he showed comparisons. talking about hotspots in protons, right?
Yeah.
So
That starts mattering if you do PP.
And even hotspots is like the simplest substructure that you could think of.
Yeah, it could be
Yeah.
could be something different.
Right, yeah, exactly.
if you start to get sensitive to this, actually, right, then
Well, so the thing,
then theory is a little.
I think also my memory of the
Little
flow in proton is it's only at really, really high complexity. So it's probably even stranger.
Turns out that
far away from the model, right?
like these for the row 3, these peripheral bins are quite sensitive to the size of the hotspots. So
That.
so that's also why we hope, like, if you fit to this, I mean, you're pretty sure hydral works here, so you can use the inference that then maybe you can trust what the hotspot size should be.
Okay.
Everything else is completely insensitive to these hotspots because it's like completely sub-leading scale, so you don't really see it anywhere. Also, I don't know why the row 3 is very sensitive to it, but it seems to be.
Okay, yeah, firstly, nice talk, and then forgive me for this ignorant question of regarding the experiments. So, when you're running these, I guess oxygen and all the things you listed, like in the which experiments, which detectors are going to be like working on this?
Wait, can you repeat last?
Will it be like, will it be ELISE or will CMS also have a go at the
Yeah, they all measure this, and then we choose what to fit to. So
okay, but my understanding is that with CMS you essentially like get it forward rapidity. That's right too?
Not necessarily. CMS can do centrals, like with rapidity stuff as well.
Yeah, I heard you talk about the difficulty of dealing with 3+1D stuff. Is this on the theory side, but the experimental side, can they go as far as they want?
Well, I mean, there's also, of course, limitations that you have to have instrumentation at these very high rapidities, which becomes more difficult. But on the theory side, it's basically that 3D is much more expensive. It's like 10 times slower than 2D, but also we don't really know what the initial condition should look like. So if you want to, I mean, of course you can try to make a fit, but then if your ansatz for how you parameterize this is just wrong, then yeah, you're not gonna really.
The numerics gets too complicated to just play around there, right?
Yeah, I mean, you can also not say like, oh, okay, I'll just parameterize it with 100 parameters, because you cannot just put 100 parameters in your Bayesian analysis.
So, but if you get the whatever, so suppose I give you the initial state. Here you go. Here's my 3D initial state model. It does this, and then you just.
Then you could compute the you can.
Is the like code already?
Yeah, we can do this, but then the problem is that you don't know whether this initial condition is correct.
Okay, but that's not the bottleneck, you said.
Well, so it's basically, so right now for us, the bottleneck is really just processing power. So we have code that is 3D capable, and we can in principle do a Bayesian analysis on that. But Bayesian analysis is very, very time consuming. As I said, like Wilke spent a month making the row 2 observable apples to apples in his comparison. Like for the 3D, those are all observables that we have never fitted to before. So we have to go through all of them to make sure they're apples to apples. If it doesn't fit, we have to figure out why does it not fit the data. And that's just very labor intensive. And for most of the, past couple of years that we've been working on Projectum, it's really just Wilke and me. So we really don't have time to do all of that. It's been on our list for a very long time, and now we have helps, and now some people in GSI are going to do that Bayesian analysis for us, but they've never done a Bayesian analysis before, so we have to teach them how to do it, which also is very time consuming. So these are all things that we are working on, but yeah, we're not magicians. We cannot just instantly do this, even though we know how to. We know how to do this fit. It's just that there are only 24 hours in a day.
Intolerable.
Damn.
I mean, at least the situation has improved. Earlier, people would ask such questions, and we just respond to like, "Feel free to do it." Now it's people are actually responding positively to that question. It's like, "Oh yeah, sure, we'll do it." And then, well, we can teach them, and then they will hopefully give us some answer.
Okay, so thanks to the speaker one more time.